got a question about the Jose story. Did I ever tell a Jose story?
No, you didn't. Never tell me things.
As long as it's not a Luis story.
So it's what?
Not a Luis. Was that the guy last year?
Oh, yeah, no.
I cannot think of it.
Jose's probably in his 40s by now, so this is a while ago. When doing motion experiments, there are various ways. We have the motion sensors, which is really nice. So it just bounces sonic wave off of it, sonar wave off of it, and it comes back. It measures how long it takes for the signal to go out, come back. It measures the distance based on that. But before that, there are two main methods of measuring distance or position with time. We're using tape, not masking tape, but long white tape, not sticky, and then you have a device which basically put a piece of carbon there, and it makes marks 60 times a second. So you get an idea as it goes faster, there's a bigger gap between the dots. The other way is using a spark timer. And spark timer is one that instead of using a piece of carbon paper to make a dot, it would do a little spark between the track and this metal wire hanging out. And it basically puts a small little burn mark. So we set it up, ran the trial, cart goes down, hits the bottom of it was an air track. You might have seen them in the lab. They're standing upright, but it's about yay tall. It's got tiny little holes in it. You turn it on, air blows through, and so the cart, not frictionless, but close enough. So the cart went down, hit the end, and it was going fast enough, it bounced off the track and fell off. And so then we put it back up to do again. Now, I wanted Jose to be involved somehow. It's hard to blame him too much for being 12 years old. I've suppressed memories of what I was like at that age, so anyway. Sorry, just so stupid of me. So I say, hey, Jose, why don't you hold the cart, and then when I say go, you let go of it. And he touches it, and he goes, ow, that hurts. Well, we'd already run this through once, and it didn't hurt anybody. I'm figuring Jose's just goofing off again. So then, Jose, come on, put your hand on that. Ow, it hurts. And I'm really frustrated at this point, because I'm thinking he's really carrying this a bit too far. And so I get some other student, I say, you hold it, and he goes, ow, that hurts. And then it hits me. Jose was not goofing off. I should have taken it seriously, and that was my bad. Then I touched it, and it hurt. Nope, Jose nailed it when he said, ow, that hurts. What happened was the cart went down. When it got down to the end of the track, it bounced off. It knocked the grounding wire off. So now the electricity is looking for a ground, looking some way of getting away, and it was going to whatever person was touching it. And that was the problem. There was no lawsuit, which was good. No one was hurt, other than, that right there. There's no one's heart stopped or anything like that. There were no deaths. But yeah, that was just bad on my part. One, I should have checked the grounding wire. Two, I should have taken it seriously when he said it the first time. So that was me violating the safety rules. The Jose story. And I hope he's happy and is not 12 years old. Questions? Not necessarily related to that, but related to the course, the class. Okay. We last left off we were dealing with motion problems.
This came up in another class, so let's assume you want the same issue. Make sure I'm not missing anything.
Ball is dropped from a height of 50 meters above the ground. How long will it take for the ball to fall? So, and it's possible that no one in this class would have this issue, but I just want to bring it up just in case you missed. There's 3 pieces of information here. There are 3 numbers we can extract. So, let's extract them. All right, so the basics that we have here, there's displacement, initial velocity, final velocity, acceleration, and time. These are the 5 basic quantities. And in 151 and 251, we have a set of equations that go with this. And we have some like here, not as extensive. But from the problem, what do we know? Which of these 5 quantities do we know?
Displacement, acceleration, and initial velocity,
Yes. What is the displacement?
50 meters.
All right. If we take that to be correct, then what did Robert just do? He has set in motion something that affects the rest of the problem. All right, let's keep going. He said we know the initial velocity. Initial velocity is not given explicitly. What is the initial velocity?
0.
Why? What's the key word here?
Initial.
What's the key word in the problem that tells you that the initial velocity is 0?
Drop.
Yeah. If the dropped by itself means I have it in my hand and I let go, as opposed to throw. If I had thrown it, then it would not be 0, but it is dropped, so initial velocity is 0, and that's the part that the student from another class, it was not immediately obvious. So this is 0 meters per second. And the acceleration, assume this takes place on Earth.
9.8 meters per second squared.
Not negative? I've got a couple of nods, yes, I've heard a no.
Positive, negative haven't been.
I guess they have.
And it's negative.
Pardon? Then what you're saying is Robert made a mistake. You wanna say that? You wanna say, just turn to him and say,
It's okay.
Robert, could you?
It's okay, it's negative.
What mistake would he have made? If the acceleration is negative, what mistake was made? This goes back to my question earlier of what was established after he told us something.
Because the initial velocity, is it because the initial velocity started at 0?
No, actually, the initial velocity being 0 is not affected by what I'm going on about.
Displacement.
So if acceleration is negative, what's the displacement?
Negative.
And that's when he first said that this was 50 meters, he was establishing down was positive at that moment. So whether down is positive or negative, and it doesn't matter which one, but whichever way you're doing it, in this problem, those two will be having the same sign. So if acceleration is negative, displacement is negative. And other way around. And if they're one's positive, the other one's positive. So they are the same sign in this problem. So do we stick with what he originally said, or do we just say, Robert, you fool, we pity you? Looks like no one's willing to stand up against you. I guess
The quality went up full.
I guess we'll keep it like this since no one's gonna challenge it. All right, so down is positive just because Robert said so. So now we have this issue of, I know how far it falls. I don't know what the final speed is or final velocity. I don't know how long it's in there, that's what I'm trying to find. How do you solve it? Well, Hewitt has specifically talks about this problem. Chapter 3, let's see, where's he put, there he is. For those who reference later, it's page 48 of the textbook. He gives the equation. D equals 1/2 GT squared. That's the equation that he gives on that page, on page 48. This equation works if it has a couple conditions. One, it assumes the initial speed is 0 meters per second. It assumes free fall. And it assumes that the distance falling is small compared to whatever planet you're near. So that the distance is much less than the radius of the planet. If you ever see the two less than symbols like that, this means much less than. So anything in our experience, like even if you're a pilot, if you drop something from an airplane, well, you have air resistance, so not that free. This actually is a specific case of a more generalized formula, and I'll just put the more generalized formula. I put this up here, you can use it if you wish, don't use it if you don't want to. There are other alternatives of using it. I have done this in the past, and there have been a couple students who've liked it and used it right, so. The displacement is equal to the initial velocity times time plus 1/2 AT squared. That is a more generalized version of this. So if the velocity is 0, that term drops out. If it's the only force acting on it is the force due to gravity, then we've got free fall there, that becomes G, and we end up with this equation here. And we can apply that to some of the other problems that we did last week, but we'll get there. All right, so let's actually solve the problem. So I know that it's going to fall 50 meters. And that's going to be equal to 1/2 times 9.8 times time squared. So this is the math problem we're working with here. I know we've got a wide variety of math background in here, so the question is, how do you actually solve it? Well, we need to solve, we're trying to find t, so we've got to peel away the layers. Sort of a reverse PEMDAS. Well, I've got no addition and subtraction, so I don't have to worry about that. Multiplication and division. Well, I've got these two hangers on here. I got the 1/2 and the 9.8 multiplied times t squared, so I got to get rid of those. How do you get rid of things that are multiplied? So I can divide both sides by 1/2. Or for some of you, multiply times 2. And we end up with 100 is equal to 9.8 times time squared. Now we got to get rid of that 9.8 by
Dividing.
and so I'm left with t squared is equal to, that's 10 point something. 10.2. 10.8?
Two.
10.2? What's 10.2? Okay. And now I have to get rid of that radical. How do you, sorry, not a radical, how do you get rid of that square?
Square root.
You do the opposite, which is the square root. And so the time ends up being the square root of 10.2, which is 3.19.
1.9.
And now we are at the end of the problem, so we need to make sure we have units. It's time, so seconds. Yeah, Jason.
This may be very obvious, but I'm having confusion. Why can't you just solve for the seconds if you're trying to find time? Like, you have 50 meters, and you know it's dropping at a rate of 9.8 seconds, meters squared, or meters per second. Why can't you just?
Because that's meters per second squared. That's the rate at which the velocity is changing.
Okay, gotcha.
So, yeah, we can't get away with just, I assume you're thinking 50 divided by 9.8? Yeah, that, if it were a constant velocity, no acceleration, and that were the velocity with 9.8 meters per second, yes. But acceleration makes it far more complicated.
Gotcha.
Other questions? All right, review some of the stuff that we did last week. Apparently there is no weight section. All right, well, forget that then. Object is moving along a straight line. A constant acceleration. Its initial velocity. Its initial velocity is 30 meters per second. After 10 seconds, the velocity is negative 20 meters per second. What is the average velocity? What is the displacement? What is change in velocity? What is the acceleration? At what time did the object stop? Distance. The object go. Is the average speed. All right, so we've got a series of questions all based upon a beginning premise. And so I would typically break it down on a test, I'd break it down into these various parts in the order in which I would solve them. If you want to solve them in a different order, well, there are times in which however your brain is working at that moment, you might want to solve them in a different order. And just, if you do that, since one part depends upon another, just give me some hint as to the order in which you did them. So if you solved displacement first and then found the average velocity, just, give some, like draw an arrow from here to here and then to here, just so I know what you are doing and I know what you are basing things on. It's just makes life simpler for me. All right, key thing there, constant acceleration. So we got a couple so find the average velocity, if acceleration is constant, how do we find that?
Initial velocity plus final velocity divided by 2.
Yep, just average the first and last. So my average velocity, again, if acceleration is constant, is v initial plus v final divided by 2. So 30 plus negative 20 divided by 2. And we end up with 5.